opportunity to give a talk. Today, I will talk about the functorial approach to n-exact categories. And this is based on a preprint which I have recently uploaded and a sequel which I hopefully be able to finish soon. And the main point of this all is basically to make the construction of n-exact categories easier. Because so far, whenever we try to construct n-exact categories, we kind of need to find an n-cluster tilting object in some exact category, which sometimes can be very difficult. So I want to reformulate the axioms basically homologically. And there is some housekeeping to do. So throughout, I will assume that n is a positive integer, and I will speak about the n-exact categories. But if you're not familiar with them, you can just imagine that n is 1. And then an n-exact category is just an exact category, and an n-exact sequence is just an exact sequence. And I'm interested in constructing n-exact structures on proj C, where C is some additive and idempotent complete category. But again, we will look at functor categories, so you can just imagine that C is a ring, and it will make everything easier. But if you're familiar with functor categories, just think of the an additive idempotent complete category. And I will denote by FG the finitely generated right C modules. And in order to understand n-exact sequences, what one really has to do is, or n-exact structures, is to understand n-exact sequences first. So kernel, co-kernel pairs in the case n equals to 1. And what one can do if one has such an n-exact sequence in proj C is one can form the defect of, so that's the co-kernel of its rightmost morphism in the module category. And then this n-exact sequence will become a projective resolution of this module. And because projective resolutions are unique up to homotopy, this defect will basically determine the sequence, and the sequence will determine the defect. So if we want to understand the sequences homologically, we basically just need to understand the defects homologically. And so then we can calculate what the possible defects are. And the first thing we notice is that because the defect is formed as the co-kernel of its rightmost morphism, they will always have projective dimension at most n+1. But then in order to say that this is actually a defect and to characterize them completely, one needs an additional condition. And this is an X vanishing condition, which will ensure that this sequence will also be an n co-kernel of its leftmost morphism. And yes, and then one can indeed show that all n+2 term resolutions of such objects are n-exact sequences. And conversely, each defect of an n+2 sequence will give us an object in this category. And then one technical housekeeping thing, one can also flip all the arrows. And then one will get a defect in mod C op. Like if I reflect all of these arrows. And in order to relate the defect on the right and the defect looked in the opposite category, one needs a duality. And this duality, it can be very conveniently described by a next. And this makes working with it very nice. And so what one can do is we look at the n-exact structures, and they are basically just a collection of n-exact sequences. And so they will correspond to some subcategory of this defect category via this forming defects. But on the left, we also have some additional conditions which have to be met. So we have pullbacks, we have compositions of admissible epimorphisms have to be admissible epimorphisms. And so this imposes some additional homological conditions on the right. And for the two things I just mentioned, one needs that this subcategory is a Serre subcategory of the finitely generated functors. And then the conditions on the left, like the dual conditions, so existence of push-outs and composition of admissible monos, it can be dealt with this duality, and one really has to only consider one side. And this is a very convenient bijection, because it's very easy to go from right to left or left to right, because if you have something on the right, you just form all the projective resolutions of all the possible objects, which have n+2 terms, and then you will get all the conflations. And if all of this looks a little bit familiar to you, then this is probably because this is a generalization of a result which has been done by Enomoto, in that case n equals to 1. And so, yeah, and so this is a generalization of this to the higher case. And now, in order to achieve our goal and to easily construct some n-exact categories, we basically just need to find this, this f in this defect category. And for this, it would be very convenient if we would not have to check this condition that, that the two subcategories are actually Serre. So it would be very nice if we had some kind of generator for this f, and we then take the extension closure, and it will automatically happen that it's a Serre subcategory. And well, this works, for example, if we take a simple object. And because if we take a simple object and we form its extension closure, then we will get something that is Serre. And we need some additional conditions, of course, because we need to lie in this defect category, and we also have to take care of the other side. So we want the simple to kind of behave nicely with respect to our duality. And so what we do in order to achieve this is we kind of mimic the properties that n+1 regular modules of, or like regular simple modules of a commutative rings have. So if we first ask that this simple module is actually in the defect category, which we will rewrite in a second, and we assume that when we apply this duality, we actually get again a simple, then we get basically what I then call an n+2 regular module. And if we rewrite what this S being in this defect category actually means, it's that it has a projective resolution by finitely generated projectives of length at most n+1, and it has this X vanishing condition. And now if you look at this, this looks exactly like regular modules over commutative rings behave. And if you know about Artin-Schelter regular algebras, this is also exactly how the simple modules of an Artin-Schelter regular algebra behaves. And yes, and indeed, when we take any class of such n+1 regular simple modules, then we get an n-exact structure. And so all the work which has been done on like constructing Artin-Schelter regular algebras, this can now be used to construct examples of this new theory of n-exact categories. And the hope is that maybe one can also use the theory of these n-exact categories and this n-exact structure to make some statements about Artin-Schelter regular algebras. And I want to close basically by giving one very explicit example of this construction. So for example, one can take the set-graded ring, polynomial ring, where we put x and y in degree 1. And this is actually one of those Artin-Schelter regular algebras. And therefore, all the simple R modules, they are regular. And then one can look at the category of graded projectives, and the indecomposable objects of this category, they are just in bijection with the object of Z. So in each degree, there's just one graded projective. And the irreducible morphisms, they can also be described just knowing this algebra. Namely, the irreducible morphisms are more or less the generators of this algebra. And one can also check, because projective resolutions of simple modules are basically AR sequences, that this category of graded projectives has AR sequences. And then if one constructs this AR quiver, then one sees in this specific case that you basically get the pre-projective component of the Kronecker quiver glued to the post-injective component. And this works in way more generality. Like you can take more variables, you can take different gradings, you can even non-commutative gradings, and it will all give you examples of n-exact categories. And it also works with the generalized Artin-Schelter regular categories defined by Solberg and Martinez-Villa, for example. Yeah. Okay, that's all. Thank you very much.